Hello and welcome to York Observatory's monthly TeleTube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alumni Carswell Observatory located at York University in Toronto, Ontario, Canada. York TeleTube broadcasts every last Friday of the month at 7:30 p.m. local Toronto time, right here on our YouTube channel. For any questions or comments you have about our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Instagram at the handle Yorku Observatory. We are pleased to share that the Summer 2025 Astronomer in Residence program has successfully concluded. This initiative, a collaboration between the Alumni Carswell Observatory and Killarney Provincial Park, hosts astronomers at the park-certified dark sky site to lead in-person presentations and shows using the park's observatory. For astronomers interested in applying, the 2026 summer applications will open in February 2026 through the AIR website. To learn more about the program and explore past astronomers' blogs, visit yorku.ca/science/observatory/AIR. Good evening, everyone. My name is Hector Jimenez, and I am here alongside Anit Dia, Darius, and Professor Mary Helen from Alumni Carswell Observatory at York University. We're excited to welcome you tonight for our final Friday TeleTube, where we will be exploring three fascinating recent stories from the world of astronomy and space. The observatory at York campus is in Toronto, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many indigenous nations. The area known as Toronto as being caretaken by the Anishinaabe Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts join the long story and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. Now, let's see what targets are up tonight. Please, Professor Mary Helen, go ahead.
Hi, so tonight, if we look at the sky, there's a number of interesting objects up. So the map we have up shows what's visible at Toronto around 11 p.m. tonight. Tonight, your chances may not be that good because it's a bit cloudy and a bit hazy, but even for the next couple of nights, these will still be there. So four things we're sort of suggesting. One is the bright star Arcturus. It's been visible for a lot of the summer. It will sort of probably disappear from view over the next few weeks because it's more of a summer star that's visible, but it is still visible right now in the northwest, not far from Arcturus. Of course, you can also see the Big Dipper because even on this screen, you can see fairly clearly, just above and to the right of, or to the left of the north, you can see the Big Dipper. A couple of other objects. Vega is about the brightest star in the sky, and you can see it's up near the top of this map. It's fairly actually close to the top of the sky right now, and you'll see close to it two other bright stars that are Deneb and Altair, and these make up the summer triangle that is visible throughout most of the summer season. And even in Toronto, where the skies are fairly light polluted, you will often go out and see this sort of large triangle in the sky, and that is Vega, Deneb, and Altair. Another object that's, of course, visible, if you can see that little blue circle that's sort of between the north and the east and just sort of below and to the right of Vega, that is, of course, the Andromeda Galaxy. It is a spiral galaxy like our own. It's about 2 million light years away, and it is about the farthest away object you can see with the naked eye. It will actually look like a bit of a fuzzy patch on the sky if you see it. And of course, the last object we have up in our list is Saturn. It's the only planet that's really visible about this time of night. But if you look to sort of the southeast roughly, you will see a bright dot. Because it is a planet and not a star, it won't twinkle, and that will be Saturn. So that's kind of what's up in the sky tonight. But also remember at the observatory, we do have public viewing online on Monday nights at 9 o'clock. Even if the weather is bad, we'll still put up images we have taken in the past, some of our best ones. And if the weather is good, we will open our 1 meter telescope and have sort of live viewing of what is in the sky. Wednesday nights, we also have observatory tours every Wednesday night. Right now, they're starting about 6:30 or 7. Depends sort of roughly what time the sun is going down. It's sort of getting earlier as we get sort of later in the year. Please check out our website for the times of these because it's sort of a great opportunity. Uh, all of these are free, but again, the observatory is sort of run by a lot of volunteers and stuff. So we do appreciate if you can make donations on our web page if you are interested. So I will pass it on to Darius then, who will go on a little, give us a bit of detail about what we're going to be discussing tonight.
Thank you, Professor. Hey everyone, I'm Darius, one of tonight's speakers. Hector, Anidia, and I are all physics and astronomy students here at York and are all a part of the observatory team. Tonight, we come to you with a few astronomy news segments for you. First off, Hector's will be about the reboost of NASA's Swift Observatory. Then my own, which is about possible signs of past life on Mars. And finally, Anidia brings us a story on a certain black hole growing faster than expected. We hope you all enjoy and take interest. Take it away, Hector.
Excellent. Thank you so much, Darius. All right, so again, good afternoon, everyone. Today I'm going to talk about a bold and timely mission, the attempt to reboost NASA's Swift Observatory using a robotic servicing spacecraft. But why is this interesting? Swift has been a productive workhouse for over 20 years, but now faces orbital decay. This mission could be the first time a private robotic craft captures an unprepared US government satellite not originally designed for servicing. It is a story of science, engineering, risk, and the evolving commercial space ecosystem. Let's see what is Swift and its mission first. The Neil Gerald Swift Observatory launched in 2004 to detect gamma-ray bursts, also known as GRBs, extremely energetic short-lived bursts of high-energy gamma photons. The GRBs may arise from catastrophic events like supernova, collapse of massive stars, or mergers of compact objects like neutron stars or black holes. Swift functions as a kind of dispatcher. It detects the initial burst, localizes it, and then alerts our telescope for X-ray, optical, or radio to observe the afterglow and further study the source. Over 2 decades, it has yielded many discoveries about high-energy astrophysical processes, transient phenomena, and cosmic explosions. Let's move on with the orbital decay and the atmospheric drag. Swift orbits in low Earth orbit, also known as LEO. Even at high altitudes, Earth's atmosphere is not a perfect vacuum. Very tenuous residual gas molecules exert a drag force on satellites, gradually slowing them and lowering their altitude. This process is orbital decay. It is usually slow, but certain factors can accelerate it. One major factor is solar activity. When the sun is more active, it heats and expands Earth's upper atmosphere, increasing density at higher altitudes and thus increasing drag. Recently, Swift has experienced more drag than anticipated, causing its orbit to drop faster. With our intervention, it faces a substantial probability of uncontrolled re-entry in 2026. Because Swift was not built with propulsion or servicing in mind, it cannot raise its own orbit. So let's take a look to the contract and the timeline. In September 2025, NASA awarded Catalyst Space Technologies, based in Arizona, a contract to design and build a robotic servicing spacecraft to rendezvous with Swift and raise its orbit. The target is to launch in spring 2026, rendezvous with Swift, dock it, and perform a reboost maneuver. This is a fast schedule relative to typical space servicing missions, reflecting the urgency imposed by Swift's orbit decay. It became a race against the clock, technically. But what about the technical challenges and the capture strategy? One big challenge: Swift is unprepared. It does not have docking ports or grappling fixtures designed for servicing. Catalyst's plan is to use a custom robotic capture mechanism that will grip small metal rims, also known as flanges, originally part of Swift's launch structure. These are not ideal for docking, but can serve as grip points. The servicer must approach carefully, perform rendezvous and proximity operations, match orbits, and maneuver to align with the grip points without damaging delicate instruments. Once captured, the servicer must fire its propulsion to raise the combined system to a safer, higher orbit. This requires careful thrusting to avoid torques or stresses. All of this must be done autonomously or semi-autonomously, with high precision and reliability. But ask yourself, why this mission matters? If successful, this will be the first time a private robotic spacecraft captures and services a US government satellite that was not designed for servicing. Secondly, it also represents a shift in how we think about satellite life cycles. Rather than discarding or losing assets, we may one day routinely service, refill, reposition, or even repair them. NASA sees this approach as more affordable and faster than launching a brand new replacement for Swift. This mission also has a broader implications in national security and space infrastructure, capabilities for responsiveness, on-orbit servicing, and maneuvering could be important assets in a contested space domain. But there are also risks and technical uncertainties. First of all, gripping the ground feature or applying too much force could damage Swift's structure or instruments. Also, navigation, control, and relative motion at close distance are delicate. Any misalignment or unexpected movement could jeopardize the operation at all. Besides that, propellant margins and thruster performance must be sufficient for capture and reboost. The timeline is tight. Delays could cause Swift's orbit to decay too far, making recovery impossible. The mission is risk tolerant, though in NASA's own words, but still depends on integration of new and test technologies. There is an alternative: letting Swift decay. NASA could allow Swift to deorbit naturally. Many spacecraft are designed or assumed to have an eventual control or uncontrolled re-entry at end of life. The trade-off is losing continuous data from Swift's instruments. Replacing its capabilities with an entirely new mission would cost far more and take more than possibly a servicing mission. Also, letting it deorbit forgoes the opportunity to push forward the technology of on-orbit servicing. What about contingency planning? NASA and Catalyst will monitor solar activity and orbital decay carefully. If conditions worsen, they may adjust the launch window or trajectory. The design phase includes simulations, risk analysis, redundancy, and fault tolerance in control systems and capture mechanisms. If successful, SWIFT can continue operation for several more years. The precise extension depends on achieved orbit, lifetime of instruments, and system margins. That means continued observation of gamma ray bursts, transient events, and serving as an alert dispatcher to the astrophysics community. We also have a proof of concept for servicing. Demonstrating an unprepared satellite reboost opens the door to servicing other aging but valuable satellites. It also might lead to a future ecosystem where spacecraft are more modular, maintainable, or serviceable by design. And summarizing and looking ahead for future, the SWIFT reboost mission is ambitious and high stakes, saving a decades-old, still valuable scientific asset instead of letting it succumb to orbital decay. It leverages commercial capabilities, rapid development, and advanced robotics to attempt something no one has done before, capturing an unprepared satellite and restoring its orbit. If successful, it could change how we treat satellites, not as disposable objects, but as maintainable infrastructure. It would also deepen US leadership in space servicing technologies. In the next 1 to 2 years, we will see whether the launch, rendezvous, capture, and reboost all work as planned. Finally, the outcome will teach us much about the future of space operations. That's about it. Thank you. And it's time for my friend Darius to talk about Mars. So please, Darius, the ground is yours.
Thank you, Hector, for that fascinating breakdown. Okay, the story I bring you today is one about possible signs of extraterrestrial life on the planet Mars. Earlier this month, the Perseverance Mars rover uncovered a rock sample with features that qualify as potential biosignatures. For those not read up on astrobiology, this term represents a chemical, clue, or physical feature or pattern that hints at some sort of known biological process that we can study or see here on Earth. In this case, there were certain geological patterns in a rock with iron, phosphorus, and sulfur minerals, as well as carbon. On Earth, we see this process happen with reactions involving organic matter and microbial metabolism. In short, the details in this rock suggest past presence of microbial life existing on the planet. It's important to note that biosignatures like these are unable to definitively prove life. They can only suggest and imply it. It is possible that these geological structures could be formed through a different means, perhaps one that we are not aware of or capable of recreating for whatever reason. To confirm biological origin, we'll need further data, ideally analysis in an Earth-based laboratory on the samples once they are returned. More measurements for isotropic discrimination would take place in these labs, and perhaps elimination of abiotic pathways. The rock in which the discovery was made was nicknamed Shayava Falls. It is part of a outcrop in a region called the Bright Angel Formation in the Jezero crater. The ground in this area contains fine-grained sediments, which are good at preserving subtle chemical signatures in low-energy water settings. The sediments in Jezero likely date to 3.2 to 3.8 billion years ago, when Mars was wetter. If life existed then, it may have left traces in exactly the kind of depositional environment preserved there. Jezero is a significant feature on Mars to search for biosignatures in, since the current theory suggests that it used to be underwater. The crater shows signs of significant flooding, including a fan-shaped delta deposit formed by water-carried sediments and minerals that only form in the presence of liquid water. So what's next? Well, many of Perseverance's collected cores, including this one, are stored for future return to Earth. Once returned, terrestrial labs can apply far more sensitive and diverse techniques, measuring isotope levels and pattern formation, and even looking for certain organic molecules. This is a very important discovery because it's our strongest indicator for evidence of extraterrestrial life. It may provide justification to return the samples to Earth for study and further research into other biosignatures that could be present. If the existence of past life is confirmed, it would mean that life emerged independently on Mars, or at least existed for some time, strengthening the idea that life may not be rare in the universe. It would inform life origin theories by giving a second data point for how life can begin and evolve in different environments across the universe. Furthermore, it could also reshape planetary protection policies and inform us on how to regulate our human exploration in a way that prevents contamination and preserves biosignatures on other planets and moons. That's all for that, and Anidia will begin his presentation now.
Hi, all. We're just waiting for Anidia, who seems to be having some technical difficulties getting his mic working. But he will be talking about black holes for us in a moment. I think Darius's last one was quite interesting if people know anything about the history of life on Mars, because of course, if you go back to the 1980s, that very famous asteroid ALH 0084 was found that was also suspected to have chemicals uh, that are associated with life on board. Now, it turned out in that case they couldn't conclusively prove anything, but it would be very interesting if some of this Cheyevo Falls stuff now at a later date managed to actually more conclusively provide evidence of life on Mars. If nothing else, what it does again reinforce is that Mars at one point was a wet planet, so definitely the conditions existed in order for life to flourish. I think Inidia's managed to get his stuff working, so I will turn it back over to him.
Hello, everyone. Apologies for that. Something just happened with my mic. But anyways, let's get back to the topic. So today I would want to talk to you a bit about black holes that is growing faster than expected. And the name of this black hole is RACS J032035. So before we dive up straight into the black hole, let's talk a little about the basics of the black hole. So black holes grow in two main ways. The first is through accretion, which means pulling in gas, dust, and plasma from the space around them. This material doesn't fall straight and instead forms a swirling disk around the black hole called an accretion disk. Friction and magnetic forces inside the disk heat it up to millions of degrees. so it glows brightly in X-rays and other radiations. As the gas loses energy and momentum, it spirals inwards until it crosses the event horizon, which is ultimately the point of no return. And the second way a black hole can grow is through mergers, by merging with another black hole. And when two black holes collide, they combine into one larger black hole, releasing a huge burst of energy in the form of gravitational waves. Ripples in space-time that we can now detect on Earth while observing by the observatories we have on Earth, some like LIGO and Virgo. Now, here's the problem with this thing. There's supposed to be a natural speed limit to how quickly black holes can feed. This thing is known as at the Eddington limit, named after the English astrophysicist Arthur Eddington. The logic behind it is very straightforward. As gas falls into a black hole and heats up, it emits radiation. Now, this radiation is not just light, it carries momentum. That radiation pushes outwards on the very gas that's trying to fall in. At some point, the outward push of the radiation balances the inward pull of the gravity. When this balance is reached, the black hole shouldn't be able to feed any faster. That balance point is the Eddington limit. Now, for decades, astronomers have treated this limit as a rule of thumb. Black holes can grow fast, but not too fast. But now we have found an exception. Just this past September, NASA announced results from the Chandra X-ray Observatory. Astronomers discovered a black hole called RACS J032035, located about 12.8 billion light years away. That means we are looking at it as it was less than a billion years after the Big Bang. Now, already this black hole is enormous, about a billion times the mass of our sun. Here's the shocking part. It grows at roughly 2.4 times the Eddington limit. In other words, it's not just nibbling politely at the cosmic buffet, it's gorging itself, breaking the very rules we thought govern black holes' growth. Now, how is this possible? Astrophysicists and theoretical physicists have few ideas. Now, one possibility is that the accretion disk isn't a thin, flat disk, but a thick torus, like a cosmic donut. In that shape, much of the radiation gets trapped or funneled away, meaning it doesn't push backward on the infalling gas as strongly. Another idea is something called photon trapping. If gas is falling in so quickly that light can't escape efficiently, the photons basically get dragged inward with the material, reducing the outward pressure. Both of these scenarios would allow the black hole to bypass the traditional limit. Now, why does this thing matter? Well, one of the biggest puzzles in modern astronomy is how supermassive black holes, giants billions of times heavier than the sun, managed to form so quickly in the early universe. We know from telescopes like Hubble and James Webb that such monsters already exist less than a billion years after the Big Bang. That's an incredibly short time scale in cosmic terms. If black holes were limited by Eddington rate, it would be very hard for them to reach such enormous sizes in time. But if some of them can, under certain conditions, grow faster than the limit, then the mystery begins to make more sense. Of course, the discovery also raises new question. How common is this super Eddington growth? Is this black hole a rare exception or just the first examples we have caught in the act? How long can a black hole sustain such rapid feeding before something like jets, winds, or radiation blows away the gas supply? And what does this mean for our broader picture of galaxy evolution? Since supermassive black holes and galaxies, they grow together. Now, in science, the most exciting discoveries are the one that challenges our assumptions. This black hole is doing exactly that. By breaking the supposed cosmic speed limit, it's forcing astronomers to rethink how the biggest black holes in the universe came to be. Whenever there is an exception in a theory, that just means that there is a better theory waiting to be discovered. So the takeaway from all this is very simple. The universe still has surprises in store. Even the darkest, most mysterious objects, like black hole, are teaching us that the rules we thought were unbreakable may not be so absolutely true after all. So that sums up my presentation, and that sums up the TeleTube for this month. Thank you so much for listening to us. You have been listening to the Alan I. Carswell Observatory's monthly TeleTube broadcast, brought to you by the Astronomy and Astrophysics program, which has been written and presented by the students, faculty, and alumni and friends of York University. The hosts this evening were Dr. Mary Helen, Hector, Darius, and I, Anitya. Make sure to leave any comments or questions in the comment section or live chat. All our programs are free, but if you would like to donate, see our website at yourq.ca/science/observatory/. You can connect with us on Pixelfeed with the handle @York Observatory. And check out our website for show notes, content updates, and contact info. Thank you for tuning in. Clear skies and have a good night.